Hello, welcome to all. In the previous class, we studied the application of Biot-Savart law for infinite straight wire. Today also we will apply the Biot-Savart law for the infinite straight wire, but we will follow some alternate method to do so. The plan of today's lecture is to find the magnetic field of a straight conductor by using the alternate method and to study the nature of B. As a part of it, we also study the Ampere's law. Applications of Biot-Savart law. Yeah, there are so many applications, but we are considering one application, that is infinite straight wire. We will take other applications, okay, um, as a part of Ampere's law applications. Okay. Here, what is our problem? Infinite straight wire or conductor. Okay, infinite straight conductor. Infinite straight conductor. Okay, you can see this on the slide. Yeah, you see the slide. We are taking one infinite conductor. Okay, we are taking one infinite conductor. Yeah, this is a very long conductor. Okay, here, yeah, you consider one point located at the distance x. This is the point where you want to find the magnetic induction. Why we are applying Biot-Savart law for this infinite state conductor? To know the induced magnetic field. Okay, here, say this is a L. Okay, this is a length parameter of this. Okay, here you are taking dl part of okay, this conductor. Infinitesimal. This is a infinitesimal element of the conductor. Okay. Now let us call this to be, say, R. Say R. Okay. R. Yeah, this is a wire. How much current is flowing through this wire? Current I is flowing through this long, very long wire. Okay. Long wire. Okay. Right. Here, actually, we are taking this to be theta. Okay. But which theta you have to consider here? According to Biot-Savart law, this thing. This is how much now? Pi minus theta. Okay. Your Biot-Savart angle is pi minus theta. You see the diagram for Biot-Savart law. Yeah. Okay. Suppose that you want to find the magnetic induction at the point B. Now we are taking only infinitesimal length. This is the right angle triangle. So what is R here? L square plus x square. L square plus x square. R is now according to the properties of triangles. So here we want to apply the Biot-Savart law in this case. Okay. Yeah. Now let us try to apply the Biot-Savart law here. Otherwise I will write here at the top. Here you can see the steps on the slide as well. Yeah. Now according to the Biot-Savart law, according to Biot-Savart law, dV, that means corresponding to this dl element, dV is equal to mu naught by 4 pi mu naught by 4 pi I, okay, current is IDL sin theta by R means here, yeah, IDL sin theta by R, this one is R na, okay, R square, this is sin theta. Now let us apply this to our particular problem. Okay, you need any changes over here? Yeah, one thing you have to change here. This is okay. This applies to your particular problem. This also applies to your particular problem. But in the place of theta, you have to put pi minus theta because you need to take this angle in the Biot-Savart law r square. Okay. So this is nothing but again sin theta. Okay. Mu naught by 4 pi IDL sin theta by r square. Again, you get the same expression. Okay. Yeah. So now you have dV is equal to just mu naught by 4 pi IDL sin theta by r square. Okay. Now, what are the limits of this length? Dimensions infinity. Dimensions of the conductor are infinity. Okay. Now, from the geometry of this figure, what is r? L square plus x square. Okay. And what is sin theta? From the figure, sin theta is equal to x by L square plus x square. X by this opposite by hypotenuse, that is x by r means L square plus x square. L square plus x square. Okay. Now you put this here, then you get along with r. Okay. Now your r is here according to the properties of triangles. Simply this is L square plus x square. Okay. Now I will write here dV is equal to mu naught by 4 pi I dl. What is your sin theta? I dl. Sin theta means x by under root of L square plus x square. L square plus x square. Yeah, next what is your r square? X by L square plus x square. Okay. Next you have r square. Sin theta by r square. Okay. R square means, r is this thing. R square means simply L square plus x square. L square plus x square. So now you have dV is equal to mu naught by 4 pi I dl x by L square plus x square to the power of 3 by 2. 3 by 2. Yeah, now What is your B now? Therefore, your B is simply mu naught by 4 pi mu naught I. Okay, you need not to change this. Okay, yeah, integral dl into x by L square plus x square to the power of 3 by 2. 3 by 2. Okay. Now we want to perform this integral. For this, let us take. For this, let us take. Here I am doing b is equal to how much you are getting mu naught I by 4 pi integral dl into x, okay, or x by under root of no x by L square plus x square to the power 3 by 2 dl. Okay, now we have to find this integral. Okay, now the limits are extending from minus infinity to plus infinity. Okay, this is a variable your length is infinite, where conductor is infinite conductor. So let us now try to change the variables here. Put your L, put your L, we want to change the variables now. X tan theta. Tan theta is already there now. Let us write here tan alpha. Okay, I'm changing the integrals. Then what happens to your x by L square plus x square? Okay, before that, what happens to your dl is equal to x sec square alpha d alpha. Okay, sec square alpha d alpha. Now let us substitute these things here. Mu naught I by 4 pi integral. Now we have to change the integrals, limits of integrals as well. Limits of this integral. Yeah, what is your okay? X is okay. X by L means x square. Tan square alpha plus x square 3 by 2. What is dl? X sec square alpha d alpha. Okay. So b is equal to, let us write the integrals also. Whenever L is equal to plus infinity, what happens to this? This alpha becomes pi by 2. Whenever your L is minus infinity, according to this relation, your alpha becomes minus pi by 2. So what are your limits of integration? If it is minus infinity, this is minus pi by 2. If it is plus infinity, this is plus pi by 2. We are changing the variables. That's why we have to change the limits as well. Okay. So this is equal to mu naught I by 4 pi minus pi by 2 to pi by 2. Yeah. Here x square sec square alpha d alpha by take x square outside means x square whole power 3 by 2 means x cube. Okay. Inside the brackets 1 plus tan square alpha whole to the power of 3 by 2. Okay. Now let me write here. Yeah. B is equal to, now let me write here. B is equal to mu naught I by 4 pi. Yeah. X square is here, x cube is here. So you are only left with 1x in the denominator, right? Sec square alpha d alpha integral minus pi by 2 plus pi by 2 by x. What is 1 plus tan square theta or tan square alpha? Sec square alpha. Okay? Yeah. whole to the power of 3 by 2. Now, you further simplify this 4 pi minus pi by 2 to pi by 2. Here you have sec cube alpha. Okay. So here sec cube sec square. Okay. Sec square alpha cancel. You're only left with the sec alpha. That 1 by sec alpha means you write cos alpha d alpha. Here now, what is your integral variables? What is your integral variable here? Alpha. So you may safely put this x here. Okay. Now this is equal to mu naught I by 4 pi x. What is the value of this? Cos alpha is nothing but sin alpha minus pi by 2 to pi by 2. So what is your answer now here? Mu naught I by 4 pi x. Yeah, this is sin pi by 2 minus of sin minus pi by 2. That means plus sin pi by 2. That means 1 plus 1. Okay. This is 2. Okay. So, I'm writing here now. Yeah. So, your B is now mu naught I by 4 pi x. What is this? 1 plus 1? 2. 2, 2, 2 is 4. So, your B is now mu naught I by 2 pi x. Yeah, this is what the expression for the total induced magnetic field of a infinite straight wire. Okay, as I increases, B value increases. As you move away from the wire, your magnetic induction goes on decreasing as x. Okay, why? Because B is inversely proportional to x. As you move away from the conductor, and most obviously, the magnetic induction also decreases. So this is a formula for the magnetic induction of a straight wire. Okay, this you have to remember. Very simple formula, right? Yeah. Now let us discuss an alternate method of applying Biot-Savart law for the infinite straight conductor. Okay. Yeah, this is an infinite straight conductor in which current I is flowing. Now, yeah, consider a point P, okay, located at a distance x, at the perpendicular distance x from the conductor. Now, let us consider the length L of the conductor. See, let us draw one line from this point to P. Let us call this as R. Okay. Okay. Suppose that this L is making angle alpha at P. Now let us take infinitesimal element of L here. Now let us suppose that this dl makes an angle d alpha at P. Okay. Now this is the angle we use in Biot-Savart law. Okay. This is, say, this is a theta. Okay. Now let us draw one perpendicular from here to here. Okay. This angle will be alpha. Why? Because this angle is alpha. Here, by the geometry of the figure, we have here also alpha, and from this triangle you have this side is equal to r d alpha, or d alpha. Okay. Why? Because this angle is very small. Okay. If you take tan theta in this triangle, this side by tan of d alpha is equal to this side by r. So this side is equal to r tan d alpha. Okay. for a small value of d alpha, you have just this side is equal to r d alpha, r d alpha. Okay. Now let us consider these two right-angled triangles. These two right-angled triangles. Okay. So from otherwise you call this point as O. Okay, this is A, this is B, this is M. Okay, from triangle A, B, M, cos alpha is equal to, okay, at the side, the hypotenuse means R d alpha by dl. Therefore, dl cos alpha is equal to R d alpha. R d alpha. Okay. Next, from triangle this thing AOP, here what is cos alpha? Cos alpha is equal to x by r. Therefore, r is equal to x by cos alpha. Okay. Now let us consider the Biot-Savart law. According to Biot-Savart law, okay, I'll write here. According to Biot-Savart law, dB is equal, that means magnetic field due to this infinitesimal element of length, mu naught by 4 pi I dl sin theta by r square. Okay. Now, what about this theta? This is pi by 2. You know that this is the pi minus pi by 2 minus alpha. Pi minus pi by 2 plus alpha. This is pi by 2 minus alpha. Okay, this thing. Now, what about this thing? 180 minus this thing. So, theta is equal to 180 minus pi by 2 minus alpha. This is equal to pi by 2 plus alpha. Okay. Now I will write these two equations here. Just now we got dl cos alpha is equal to r d alpha. Next step, this r is equal to x by cos alpha. Okay. I will write down here these two equations which we already arrived. Yeah. Now theta is this much, so dB, therefore dB is equal to mu naught by 4 pi I dl sine of this thing, sine pi by 2 plus alpha by r square. Okay. Now this is equal to mu naught by 4 pi I dl, this is I 90 plus alpha of alpha by r square. Okay. This is dB. Then what about B? What about B here? Integral dB is equal to mu naught by 4 pi integral I dl cos alpha, because we want to know the total magnetic field induced by the conductor. Okay. On this side you have B is equal to, I is also constant, mu naught I by 4 pi. Inside the brackets you have only dl cos alpha by r square. Okay. Now yeah, let us use these two equations here. Okay. What is dl cos alpha? We just write for that. B is equal to mu naught I by 4 pi, okay, integral, what is dl cos alpha? R d alpha by r square, okay, r 1 r cancel, so you have mu naught I by 4 pi, okay, just dl by r, okay. But what is r here? You take this here, you substitute r value here, then you get here b is equal to mu naught I by 4 pi, okay. Now this is 1 by r means cos alpha by x d alpha, okay, right. Now we have to substitute the limits for alpha, okay. For this L, you have minus infinity to plus infinity. Then what are your angles for alpha? What are your angles for alpha? What will be the alpha? Okay, it can be maximum up to 90 degrees. Okay, if it is going to the infinity, okay, your dimensions of your conductor are from minus infinity to plus infinity, then this its pi value, alpha value will be from minus pi by 2 to plus pi by 2, minus pi by 2 to plus y by 2, okay. Then you may write here minus pi by 2 plus pi by 2. Now this is equal to mu naught I by 4 pi, x is also constant here, okay. Inside the integral symbol we have cos alpha, so integral of cos alpha is sin alpha with limits minus pi by 2 to plus pi by 2. So this is equal to mu naught I by 4 pi x. How much is this? 1 minus of minus sin alpha means plus sin alpha means pi by 2. It is also 1. So you have mu naught I into 2 by 4 pi x. This is equal to 2 to the 4. That's why you have mu naught I by 2 pi x. Therefore, I will write here b is equal to mu naught I by 2 pi x. Okay, you may compare this formula with the formula we obtained in our previous method. There also we got the same formula, okay. So you may use any one of these two methods to apply Biot-Savart law. So this b is inversely proportional to this x. Okay, you see in this formula we don't have any r, okay. For every r there will be corresponding perpendicular distance. So this field depends on that distance as well as current. If you increase the current, then the magnitude of total magnetic field also increases at the same point, okay. Otherwise, if you increase this distance, the perpendicular distance, or as you move away from the conductor, then what happens? It's the induced magnetic field falls as x, okay, right. This is about the application of Biot-Savart law for infinite straight conductor, right. Yeah, next let us go for the other topic. Yeah, what is our next topic? Our next topic is to study the nature of the magnetic field or the magnetic induction vector, okay. In order to do this, we have to consider two theorems. One is Gauss law of magnetism, another is the law of circulation of B, or Ampere's law, or Ampere's law. Okay, let us first consider the Gauss law of magnetism. What is Gauss law of magnetism? You know the Gauss law of electrostatics. Okay, what is that? Integral E dot ds is equal to q by epsilon. Here, this is a charge responsible for the electric field. Okay, here, how to write the similar law or the same Gauss law for magnetism? Here, we replace this E with B. If you really have the magnetic charges, then that will be some charge by q by epsilon naught. But here you have always 0 on this side. That is what the nature of magnetic field. That is what the nature of a magnetic field. This is called what we are studying, nature of B. Okay, what is this? This is Gauss law of magnetism. Gauss law of magnetism. Okay. In which form you are observing the Gauss law? In the integral form. Why? Because integrals are there. In the electrostatics, we converted the Gauss law from integral form to differential form. Here also, you may convert this integral form into differential form. Okay. On the other side, you have 0, no problem. Just you convert this surface integral into some other integral, volume integral, then you obviously get the differential form of this Gauss law of magnetism. Okay, so whenever you write from the Gauss theorem, of vector analysis, integral B dot ds is equal to surface, it converts surface integral into volume integral. Say this as V div B d. Therefore, in the place of B ds, you may write integral div B volume integral dv is equal to 0. That means you have here just div B is equal to 0. Div B is equal to 0. What is this form? Here div means, here div B means del dot B. In electrostatics, we got the formula del dot E is equal to rho by epsilon naught. Here, in magnetostatics, we have the formula del dot B is equal to 0. We call this form as differential form of Gauss law of magnetism. Gauss law of magnetism. Okay, this is integral form of Gauss law of magnetism. Okay, here you have integral form of the Gauss law of magnetism. Here you have differential form of the Gauss law of magnetism. So we want to study the nature of a magnetic field by using this Gauss law of magnetism. What does this convey? What does this convey? It conveys that whenever you have divergence 0 for a vector, then we call those vectors as, or those fields as solenoidal field. So B is what type of field? Therefore B is a solenoidal field. Within the field, wherever you may go, the divergence will be 0. All throughout the field, divergence will be 0. Then we call that field as solenoidal field. So our field B is a solenoidal field. But electric field is not the solenoidal field. What is the importance of this Gauss law of magnetism? In electrostatics, Gauss law will give you the electric field of the source of that field. That means it expresses electric field in terms of the source charge. But here on this side, on the right hand side, we have 0. What is the meaning of that? We have no magnetic sources. Our total magnetic flux is 0 around a closed surface. Total magnetic flux is 0. Total magnetic flux coming out from a closed surface in the magnetic field is 0. Okay? You can see the statement on that slide. Okay. What is the meaning of that? You can see this by taking the concept of field lines. Why? Because this is nothing but the flux. Magnetic field, wherever you take your closed surface area, the total flux will be 0. Why? Why? Because these magnetic lines are not discontinuous. They cannot go to the infinity like electric field lines. This happens when you have an isolated north pole or south pole. It's like this. We have 1, 2, 3, 4, 5 lines are coming out from the. You observe the 5 lines coming out from this closed surface. So you have non-zero flux. You would have non-zero flux if you already have a single north pole or single south pole. Okay. Otherwise, but if you put some south pole here, what happens? Yeah, this line goes over like this, going out and going in, going out and going in. What's the meaning of this? Total flux is 0. As long as you do not have a single pole or magnetic single monopole, always the net flux will be 0. So in any case, you never have isolated magnetic monopoles in the universe. That's why always the RHS of this equation should be 0. Always we have 0 on the RHS of the Gauss law of magnetism. Why? Because you cannot separate this north pole and south pole. If you try to separate the north pole from the south pole, what happens? You may not be getting the north and south pole separately, but you may be getting 2 small magnets with north and south poles respectively. So physically, it is not possible to separate north pole from the south pole. What is the meaning of that? The total magnetic flux is 0. So always, whenever you go for any magnetic field, then consider a closed surface, there you do not observe any net flux coming out from that surface. It means integral BDS will always be 0. What is the other statement of this law? There exist no magnetic monopoles in the universe. We can also state this in a very advanced manner like this. Okay, I already explained to you why the total flux is 0. Why? Because always north pole is accompanied by the south pole. That's why you always have the total flux 0. This is what the nature of magnetic field. So theoretically there is no problem. You can predict a monopole, but practically we do not observed. Nobody has on today observed the magnetic monopoles, isolated magnetic uh, monopoles in the universe. That's why we always take integral BDS is equal to 0 in conformity with the experimental results. Okay, yeah, this is what the nature, solenoidal nature or vortex nature of the magnetic field. Okay, next, let us go for another law giving the nature of magnetic induction vector. Okay. Yeah, what is the next other law? Is Ampere's law. Okay, most of you are already familiar with this law, Ampere's law. Yeah, what is Ampere's law? It is in magnetic field. We saw that the circulation of electric field is always zero. If you calculate the electric vector around a closed curve, then you always get zero. But here that does not happen. Here that does not happen. Okay. On RHS side, we always have some non-zero value. In electrostatics, you have circulation of E is zero. What is the meaning of this? Curl of E is zero. But in magnetostatics, this does not happen. Okay. If you take the line integral of B around a closed curve, then it is equal to the mu naught times that of the current linked with the area bounded by that curve. Okay, or the current linked with that curve. Okay, closed curve. We are taking a closed curve. We call this a circulation of B. This is mu naught I. It is equal to the total current linked with the curve. I is the total current. There may be so many currents within that curve. Yeah, this is a curve. Okay, so many currents may be there. I1, I2, I3, like that. Okay, you may have so many currents. See, this is I1, see, this is I2, something like that. Okay, then what is your total current? I is equal to I1 plus I2. This I should be I1 plus I2 in this case. If you want to take the line integral of B around this closed curve, that is equal to mu naught I. What is it? This is the integral form of Ampere's law. Now let us convert the integral form into the differential form. This integral form B dot dl is equal to mu naught I. Okay, now let us consider LHS integral dl. Okay, now let us use Stokes' law. Using Stokes' law of vector analysis, then your integral B dl, Stokes' law relates linear integral with surface integral, is equal to curl B dot ds. Okay, now whenever you go for the RHS is mu naught I. Okay, in the electrostatics we defined some quantities sigma rho, okay, lambda. Here also we may define similar quantities: charge, charge density, current, current density. Okay, here you may write this as current density times of ds, j dot ds, j dot ds. Okay, so whenever you substitute this LHS and RHS values in the integral form of Ampere's law, then you have integral. Yeah, I will write here LHS. This thing curl B dot ds is equal to mu naught integral j dot ds, j dot ds. So you may write this now as curl B is equal to mu naught j. Curl B is equal to mu naught j. That means del cross B is equal to mu naught j. This is the differential form of Ampere's law. So in this way we may convert the Ampere's law from integral form to differential form. Yeah, so what is the differential form of this? Del cross B is equal to 0. In case of electric field intensity, you have del cross, otherwise del cross E is equal to 0. In case of electric vector, you have del cross E is equal to 0 or curl E is equal to 0. That means your E is a irrotational field or conservative force field, but that is not happening here. That's why your B is not the irrotational field, but it is a solenoidal field. Whenever you have some del cross quantity is equal to 0, then this quantity may express this as a grad. That's why we defined E is equal to minus of grad phi. Now you do not have phi. Why? Because on this side you do not have a 0. So magnetic field is not the potential field or the conservative force field. Here we do not have magnetic potentials corresponding to the magnetic induction B. That is what you have to know. That is very important thing. Okay, that's why our B is not the conservative field, or our B is not the irrotational field, but it is a vortex or solenoidal field. It is a solenoidal field. Okay, this is what the nature of B. See, from the Gauss law of magnetism, we noted that total magnetic flux from the closed surface is 0. This is nothing but the nature of B itself. Why? Because we do not have magnetic charges, isolated magnetic charges in the universe. That means we do not have isolated monopoles in the universe. That's why the total magnetic flux is always 0. Okay. In electricity, you have both isolated positive and negative charges. You can easily isolate. But here you cannot isolate the north pole from the south pole. That is what the difference between electric field and magnetic field. What is the other difference between these two fields? Okay, here your electric field is a conservative force field. That's why you are defining electric potential corresponding to the electric field. Here The curl is not zero or the circulation is not zero. That's why that's why you do not have the magnetic potentials corresponding to the magnetic field. Why? Because B is not the rotational field, okay, or conservative force field. So it is not possible to define the potential in this case. Okay, right. This is what the nature of magnetic field. This differences you have to note between the magnetism and electrostatics. Magnetostatics and electrostatics. Okay, here these two laws can be applied for non-static cases as well, for the Gauss law and this Ampere's law. Okay, that we will be discussing in the other units. Right. Now this is about the nature of magnetic field vector, the magnetic induction vector, the magnetic field B. Okay, let us stop with this. Thank you.